Yes, I can hear you. Awesome. I can see you. Amazing. All right, everyone. Welcome back. We are back after the coffee break, and we have Nikolai here. I think, am I pronouncing your name okay?
Yeah, it's fine.
Okay, awesome. Thank you. So he's here to talk to us about scalable geospatial data science with Python and open source projects. So take it away.
Yep, thank you. Um, Can you see my screen?
Yes, we can.
Perfect. Okay. So hi, I'm Nikolai. In this talk, I want to present an overview of the tools for scalable geospatial data science. So we're mostly focused on open source projects and vector data. And so when we talk about big data, um, the first thing the first definition that comes up is like data that is not fitting on one computer. So you would need multiple machines or like a big machine to run with such a data. And just as a short, smaller example, you could take OpenStreetMap, for example, which has like about 7 billion nodes and 700 million ways, over 7 million relations. And if you would take that whole data set and extract it on your computer, you would end up with about over 1 terabyte XML file, which for most people that would fit still on a computer. But if you would run like difficult queries over the whole data set, you'll quickly run into some bottlenecks. And in order to work with that, the first solution would be to work with Postgres. And so generally, when you work with Postgres and you want to work with geospatial data, you generally use the PostGIS extension. And even if that doesn't fit your data set, you can um, still go over and use the parallelization, which since Postgres 10, it's by default enabled. And since Postgres 12, you have it by default enabled with PostGIS free. So you would have parallelization out of the box. But even when then data is too big, you still want to scale it. Another option is to use columnar storage, which is using a torrent data wrapper, where instead of storing the data in rows as you would usually do in a database, you would store each column after another, which would make analytical queries where you would calculate, for example, the mean or the standard deviation of or something like that over a whole column. You would do that much faster by scanning over one column instead of the whole table. And another option would be to use GPU processing, which you can do with pgstorm. And you can also put it on multiple servers where you have CitusDB and PostgreSQL. But generally, when we talk about big data, we most often talk about Hadoop. And Hadoop is like this massive ecosystem of tools and frameworks surrounding big data. And so basically, it came to be by the following papers. So Google published 2003 the Google file system, and shortly after it published a paper for MapReduce. And these two papers inspired the Apache Nudge team to create Hadoop, which was then 2007 used already by major tech companies as a distributed file system. And then 2008, it became the Apache Foundation project. So already we have a decade-year-old project, which is already quite impressive by itself. So to understand the ecosystem would take way too long to explain, but in a short explanation, you would have the Hadoop distributed file system, which is the file system that distributes the data and replicates it across multiple nodes. So for example, like 100 nodes, 1,000 nodes for terabytes and petabytes of data. And you would have this, if one of these nodes breaks, it would automatically reshuffle the data in order to stay resilient. And when you work with a distributed data set, you need to have a different kind of approach to work with that, and they use this MapReduce methodology. And then you need to have a manager that manages the whole thing. And this is a Hadoop yarn, which basically manages each job to go to which machine and knows where the data is located. And since this ecosystem is quite, so working with MapReduce is quite difficult, and writing these jobs and these queries takes a lot of time, and then optimizing it is even more difficult. That's why this project, the PurchaseBar, came to be, where which was created in 2009, and this is the paper for it. And it's this distributed compute engine which runs on top of Yarn, or you can also run it standalone. But generally, they use it on top of Yarn, and it's written in Scala. It has bindings for Java, Python, and R. And you would run their queries with Apache Spark, which would look like an SQL query, for example, or you can use functions that look similar to pandas in Python. And Apache Spark itself doesn't offer any geospatial capabilities by itself. So that's where Geomesa comes in. So Geomesa is a tooling for geospatial processing, where you have indexing and spatial functions that you can use. And it uses a space filling curve to index the points and data on in the data set. So like points that are closer together are on this index also closer together. And just as a short example, so this is how Hilbert curve will look like. So you can see points that are close in a similar region would also fall in the similar index of the curve. Exactly. And commonly it's used with Accumulo, HBase, and Cassandra, but it has a bunch of other databases that can be used for that too. And also, as I said before, you can use it with Apache Spark, where you have like a bunch of functions that you can use for it. Just as a quick note, here you would see like you have all the common functions that you would use in PostGIS also. And you can also integrate it with GeoServer to display the data on a map then later. So we talked about the two major elephants in the space. So what are the solutions that are not using Postgres or Hadoop? So one project that uses also Hadoop and other databases is called Presto, which was quite easy to set up. And it works in a very similar fashion to Apache Spark, where it's a distributed compute engine where you can have multiple nodes on multiple servers, where the Presto would calculate a query plan for your queries and optimize it in a similar way as Apache Spark would do. And you have a lot of connectors to all kinds of databases like Postgres, MongoDB, Elasticsearch, and of course also all various different Hadoop connectors. And it also offers a bunch of spatial temporal functions, and also uses R3 indexing. So I can also show here the various different. So you have also the similar functions that you could use like in PostGIS, with some restrictions since you're working with the distributed data. And then you have Dask, which is a Python project. It's also it also can run on one node, on multiple nodes, or even on the GPU. And so it's basically quite easy to use. It's you can basically directly use the pandas functions that you would use normally, but it would automatically parallelize it over the cluster. And then you have GeoPandas, which you can use together, which is basically the go-to library for geospatial things in Python. and it's by itself already very optimized to run quite complicated queries quite fast on a single machine. Of course, you also have the R3 spatial index for Python 2. And then there's this project that I found where Dask and GeoPandas work together. So far I haven't tested it yet, but this would basically run spatial joins on a distributed machine. And then we have Elasticsearch. So Elasticsearch it's a document store which with a search engine included, and it has its own ecosystem. It's not fully open source, but all the stuff you would need is basically open source. And it offers various indexes. So before it used geohash and a quad tree index, which were called geohash prefix tree and quad prefix tree, which was adapted to use their inverted index pattern. And now, since recently, we have this BKD tree, which is block KD tree, which uses a triangulation in the background, which is apparently much faster than the old indexing. But it only offers a few selection of functions like the geobinding box, a geodistance, geopolygon, geoshape. So not such an extensive set of functions like we saw with Geomesa and PrestoDB. Another document store is MongoDB, which also, like Elasticsearch, can be run in a distributed fashion. It offers a geohash index. It used to offer this geohaystack index, but it's deprecated now. And you index basically either over a plane, like in a 2D index, or over a 2D sphere where you index over the globe based on latitude and longitude coordinates. And the geospatial queries are similarly short and like similar few like in Elasticsearch, like only the most important queries that you would need. The last database that I wanted to show is the redis. It's like a in-memory database which can be also distributed over multiple nodes, and it's generally used like as a message broker or in a cache, where you would store data that you would frequently use in Redis, and then persist it to a different database later on. It uses a plain old geohash index, and it has a quite limited set of geospatial commands. But I recently found out that Geomesa also can integrate with Redis, so this would allow it to use much greater range of functions than before. So let's see how we're with the time. Okay. So to show some of the projects, I did some, like a cooking show. I presented some calculations before. So let me check. Okay, so here, this is an example with Spark and Geomesa. So here I use the GDEL dataset for events. It's like a event database with events across the world, like articles and things like that. And I used this data set here as an example for a big data set. And here's how this would look like. So we have this whole range here is like the boilerplate code where we integrate the jar files and set up the Spark session and initialize the configuration. Here we load the data set, which in this case is a Parquet file on HDFS. And here would be a simple query where we query in the extent of Austria, and we would then get the counts in this area by so the number of events by event root code. So then the classified event code within this bbox bounding box area. So when we run it, we see it here, and if we check it, this would be the details for the whole job. So Apache Spark runs in the background an optimization for the query, and you can see this would be the whole all the steps the algorithm would take to calculate this simple SQL statement. So normally you would write this whole thing yourself, but Apache Spark takes this away from you. And here's a more complicated query. This is a spatial join. So we have the countries of natural Earth over over a smaller set of the GDELT. So only for the 1st of January. And here we have the same small query, and then we can see that this would be like the more complicated spatial join that is optimized to run on Spark. Okay. So how would this look like in Presto? So Presto is slightly simpler in the setup. So you basically you have this cluster running with 3 nodes in this case, and once it's running, you can connect to it with either one of these libraries, and you would connect here. In this case, it connects to a Hive cluster, so it's a Hive service. And here you can see the tables there. Here define a helper function to display properly, and here we would have a simple query where we count the events in general. So here are all the counts, and we can then check here, somewhere here. I run quite a lot of queries. Just a second. Okay, this query is too old. I don't have it. But here I have here I can show like some examples of queries. So here you would use the lat long as an SD point, and you would get the geometry. And then we can query all the points within Austria, as we saw before with Spark, and this would be the query for this whole thing. So it looks quite similar. It's a similar style of query, and I hope I find it this time. No. Okay, I think this was a different session. Okay, let's see this query. Yeah, so you can also use Bing tiles in the queries, which is quite useful when you want to calculate like a 2D histogram of the whole data set, which would look like this. So we can directly use the Bing tiles as a geometry and use it then directly in GeoPandas to visualize the query. And here is like a more complicated query where we have a spatial join over the countries, where we later get back the geometry of the country. And the query will look like this. So you can see here's similar like in Spark, we have a live query plan where we can see that here he uses this spatial inner join here, and then he uses all kinds of different functions that you would normally have to write yourself, but it takes it for you. Okay. Just 1 second. Okay, I did get faster through it than I thought, so I thought it would take much longer. So I'm actually open for question now.
Oh, okay. So we have a question from Gabriel. So he wants to know if you would share those notebooks with us.
Yeah, now it's quite an ugly code as you saw in my notebooks before, but once I clean them up, I will share them.
Okay, awesome. Uh, so let me also check Discord. I think we have anything. Actually, I had a question. So like, so you talked about how we when Postgres or PostGIS does not scale out for you, you move to like Spark, GeoMesa, or like other big data, like these things which can handle big databases, right? So how do you know when you would actually want to move from having just like a Postgres database to something to the scale of a GeoMesa or HDFS or something like that?
Yeah, so generally the rule of thumb is to, if you have data below a terabyte, you shouldn't even touch it because the overhead setup for Hadoop is massive, and it takes a long time to get it configured right, set up right, and installed on each machine. So generally, when you start in the terabytes of data and then later petabytes of data, that's more or less the best range for it. When you use Elasticsearch, you can use it both for smaller and bigger data too.
Okay, awesome. Actually, yeah, I had also another question. So, have you also explored GeoWave, and what do you think is the difference like between GeoMesa and GeoWave? Have you explored that?
Um, so Location Tech offers quite a few solutions. To be honest, I don't exactly know what GeoWave does. I know GeoTrellis is mostly used for when you do uh, raster data. So um, that's all I know for there.
Okay, cool. Actually, we have another question from Terence. Have you compared performances between the solutions you presented? Did you feel an important improvement from one solution to another?
So yeah, this was like the most work to like get it running. Um, the best performance for me, which was quite surprising, was with PrestoDB. This worked out of the box, and you could immediately do like spatial joins. Um, Another one which worked really good is Dask. Dask worked really well for distributed data sets. I actually use Dask to like pre-process the data, so it's a bit clean, since GDAL is a bit difficult to work with. And Spark itself, uh, I didn't get it quite running with the HBase yet, so I'm hoping there to get some improvements from HBase. When you use GeoMesa with file system, is apparently not so fast because it's using the Parquet files as a store.
Okay, awesome. Uh, cool. I think we have some time left. And yeah, I'm just going to wait a while if anyone wants to ask Edwin, Nikolai, any questions. uh, so, so please. Oh, we have another question. Awesome. So, oh, Terence said thank you.
You're welcome.
Just check.
So I'll
Okay,
be
so I think
the
this will be
whole
the
2 days here for any questions if anyone
yeah,
has.
yeah, that's awesome. Yeah, so feel free to ping Nikolai on Discord or on the chat in the channel to have if you have any questions. And also, this was a really interesting talk, and specifically for me too, because I am also currently working as a data engineer, like to work with these data sets. So it was really like interesting for me too. So thank you very much for your talk,
Yeah,
and yeah, and it would be awesome if you could share those notebooks with us. Like once you get through
yeah.
what you want to do, like it'll be awesome if you could share it. So yeah, amazing.